Okay, so talking today about everything that is not carbon in organic molecules. What does the name, how does the name change? How does the functionality change when we add things like sulfur and oxygen and phosphorus and nitrogen and other things? So functional groups is what we're talking about. Take a second and write this down. Okay, so a functional group is a portion of a hydrocarbon molecule where a specific group replaces a hydrogen or carbon and gives the molecule radically different properties. So if you take a hydrogen off of a carbon and instead put an oxygen there, like an oxygen-hydrogen group, now you have an alcohol instead of hydrocarbon, and that's what changes ethane, which is a volatile organic compound that's you could use as a cleaner or something like that, and turns it into ethanol, which is something that certain people put in their beverages. And so functional groups, the only difference is it takes off some simple part of the molecule and adds complexity to it, right? And it changes what the molecule does, it changes how it behaves. There are three basic kinds of functional groups. There's an alkyl side chain where you just add more carbon and hydrogen, but you've got a branch now. So instead of it being a linear molecule, now it is like a T, and it's got something that comes off the side. And that's called an alkyl side chain, and I'll show you how to name that. That doesn't change the functionality all that much. It's still just carbon and hydrogen, but there's more of it, and it's not a straight line, okay? Then there's functional side chains, where there's something else besides hydrogen stuck to the side, like an oxygen, like a sulfur group, like a phosphorus group, like a nitrogen group. And those definitely change what the molecule does. And then there's main chain groups where instead of just being carbon, 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 carbon all through the chain, there'll be something in between, like carbon, oxygen, carbon, 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 carbon. And that oxygen in the middle changes what the molecule does and how it behaves and its chemistry. So there are things you stick on the side that's more carbon and hydrogen, things you stick on the side that are not carbon and hydrogen, and things that you can interrupt the chain with in the middle of the molecule. So let me give you some examples here. Oh, just kidding. Let me give you more text. So an alkyl subgroup is named like a main chain, but with the suffix -il. So there's ane, and there's ene, and there's eine. And then there's -il. And -il means this thing is hanging off the side. Okay? And so it lets you know that we've stuck something on the side of the molecule that's more carbon and hydrogen. And we number its placement along the chain. We number it so that it has the smallest numbers possible. So if there's a long chain and something is stuck, the second carbon from the end, there's a branch, then we would name that 2 something -il, and then whatever else the molecule is called. We wouldn't start counting from the other end where we have like 9 or 10 something -il, and then whatever the molecule is called. So we number so that we get the lowest number possible. So in this example here, there's 1, 2, 3, 4, 5 carbons in the main chain, and there's no double bonds. So that's pentane. But on the second carbon, we have another carbon and its associated hydrogens. So 1 carbon is meth, right? Methane, if it were just CH4, just carbon and hydrogens, it would be methane. But because it's hanging off of the second carbon of a pentane molecule, this is 2-methyl pentane. 2 because it's the second location of on the main chain at 5. Meth because it's 1 carbon. Ol because it's a chain. And then pentane, we name the normal molecule that follows. 2-methyl pentane. This one, 3-methyl pentane, we stuck the other hydrogen carbon group off of the third molecule. And notice here it doesn't matter where you start counting. This is 1, 2, 3 or 1, 2, 3. But so it doesn't really matter which end you count from. But this is 3-methyl pentane. The difference between this one and this one is where that other group is stuck. Now we call this one 2-methyl, not 1, 2, 3, 4-methyl, because we want the lowest numbers possible when we name this thing. Okay? So if it's an alkyl group, we name whatever that molecule would be. We say ol, and we stick it onto the main chain, and we count along the main chain for where it's joined, and use the smallest number possible. So we count from the end that gives us the smallest numbers. Okay. Alkyl subchains don't change the properties of the molecule a whole lot. It still basically behaves like a hydrocarbon, right? It has a low boiling point. It smells. It's flammable. These sorts of things that are true of most hydrocarbons, organic molecules. Here's some practice. So this main chain has 1, 2, 3, 4, 5, 6, 7, 8, 9 if I count this way. 6, 7, 8 if I count this way. So 9 is the longest chain. And if I count from this end, I wind up having 1, 2, 3, 4, 5, and 6 be the numbers that I use. If I count from this side, I have 1, 2, 3, 4, and 5 be the numbers that I use. So I'm going to use 4 and 5 because they're small. And here I would say that this chain down here, this is only 1 carbon, so it's methyl. But the one above is 1, 2 carbons, so it's ethyl. So I'm going to count from this side. I'm going to put them in numerical order. So this is 4 ethyl, 5 methyl, nonane. Okay? Nonane because the main chain has 9 carbons. Ane because it's all single bonds. 4 ethyl because on the 4th carbon there's 2 more carbons hanging off. 5 methyl because on the 5th carbon there's 1 more carbon hanging off. 4 ethyl, 5 methyl, nonane. Okay? That's what that is. Here's another one. So count the longest chain you can get. 1, 2, 3, 4, 5. Doesn't matter which of these you call 5. They're all the 5th, right? So 5 carbons in a row is pent. They're all single bonds. Pentane. So I have 2 things on carbon 2, 1 thing on carbon 4, or I have 1 thing on carbon 2 and 2 things on carbon 4. 2 2s is a smaller number than 2 4s. So I'm going to start counting over here. And I have 2 ethyl groups. Now, 2 methyl groups. So I say dimethyl. There's 2 methyl groups, dimethyl. And here I have another methyl hanging off of 4. So this is 2,2-dimethyl 4, 2,2,4 trimethyl, right? Because that's all 3 methyl groups and they're stuck on 2, 2, and 4. 2,2,4 trimethyl pentane. 2,2,4 trimethyl pentane. There might be other ways to name that, but there it is. 2,2,4 trimethyl pentane. Here's another one. Okay, now, longest carbon chain I can get, 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6. So 7 is what it's going to be. Now this is 7, so it's hept, but it's not heptane because there's a triple bond. So this is heptene. Or heptine, sorry, heptine. Okay?
Why do they call it hepatitis? Hepatitis.
Hepatitis is the inflammation of your liver. Has nothing to do with maybe organic molecules. Hepatitis.
Yeah.
Okay. Shh. Don't make fun of the child. Okay. So it's 7, and so it's heptine. Now, I have to, because I've said it's heptine, I have to say where the ine is. Where is this triple bond? If I count from here, I have 1, 2, 3, 4, 5th carbon. If I count from here, 1, 2, 2. So this, the main molecule is hept2-ine. Hept2-ine. And now off of atom number 1, 2, 3, 4, I have a methyl group. So 4-methyl-hep-2-ine.
What?
And
Oh
off
my
of the
God.
4th carbon, I also have an ethyl group. So this is 4-methyl, 4-ethyl-hep-2-ine.
Oh my God.
Aren't you glad that we don't name children this way? And they're like, now where's his toes attached? We're going to call you, and no. Okay.
Everybody would have the same name.
Okay. Oh wait, that's a typo. It shouldn't be ine. It shouldn't be ene. It should be ine because that's a triple bond, not a double. Typo. 4-methyl, 4-ethyl-hep-2-ine. Yep. Alrighty. Take a moment to write this down. Okay. Functional group side chains, not alkyl side chains. The first one we're going to talk about is alcohols. This is an oxygen and a hydrogen that's replaced some hydrogen on the side of a organic compound. So R, it represents the rest of the molecule, right? Somewhere there's a big nasty molecule, and then there's an oxygen and a hydrogen hanging off of it. So we name alcohols based on whatever the organic compound is, methyl, ethyl, propyl, butyl, whatever. Ane or ene or ine, whatever it needs to be. And then we say all at the end, OL, with its numbered position. Where on that molecule is the oxygen stuck? And so some molecules you don't need a number, like methanol is 1 carbon with an oxygen and a hydrogen. So you don't have to number that because it's only 1 carbon. Ethanol is 2 carbons. One of them has an oxygen. It doesn't matter which. You don't have to give it a number. There's only 2, and one of them has it. So that's easy. But we start having to number it at like propanol. You'd have to say 1 or 2 propanol to show if the alcohol is in the middle of the 3 or is at the end of the 3. Okay. So we number it, and we'll say all at the end. Alcohols. Why do we use alcohols? They're polarizing. They like to mix with water. So if you have an organic molecule that you need to make water soluble, sticking an OH group on it is a good way to do that because the OH group makes the molecule polar, lets it dissolve in water. Or not dissolve, but lets it mix with water. They're also good solvents. A lot of alcohols are used as cleaners or used to break down fats and things like that. And they're a biological fixative. If something is bathed in alcohol, the tissues die and it stays the way it is. So in those boxes right there are cats. And those cats are not decomposing because alcohol has helped make that possible. The best kind of cats you can own right there. So alcohols in OH group. Halides.
Where?
Halides are where you lift off a hydrogen and you replace that hydrogen with a halide, with a fluorine or a chlorine or bromine, etc. And when we name those, we'll just say chloromethane or chloroethane or whatever. We'll just say it's got chlorine in there, right? And you should number where it is. Ketones. Ketones, you have a molecule that somewhere along the chain, there's a carbon that is double bonded to an oxygen. So this carbon doesn't have any hydrogens on it. It's just double bonded to an oxygen and then to the rest of the carbon chain as it goes on. Okay? We name these by numbering where it is and saying "own" at the end. So if this is butane, if it has 4 carbons, and on the second carbon it had a double bond to an oxygen, then that would be 2-butanone, okay, or butane-2-one if you had other numbers that you needed to worry about. And so that tells you that on the second carbon there's a double bonded oxygen. These are very strong solvents. Alcohols are solvents. Ketones are much stronger solvents. They're even more polarizing, so they mix with water even better. They're incredibly reactive. So organic chemistry that uses ketones, you see lots of reactions happening rather quickly. They're very reactive molecules. So practice naming these things. Here I have 4 carbons in a row. Hey, look, we just did this. 4 carbons in a row, and on the second carbon, a double bond to an oxygen, no hydrogens. So this is a ketone group, and it's on the second of 4. So this is butan-2-one. Butan-2-one. And that lets you know there's a ketone group on the second carbon. Okay? This is 3 carbons with all single bonds. So propane, and the middle one, so it's number 2 no matter where you start counting. This is propan-2-one. Okay? Oh yeah, and there's a special case here where if something is right in the middle, and it doesn't matter where you start counting, sometimes they use the word iso. So they could say isopropanol, and that means right in the middle of that molecule is a ketone. You could also have isopropanol. Okay. So name that for me, somebody. Two is F. Ethane, because there's only single bonds. F, because there's 2 carbons. But it's not a ketone group. It's an alcohol group. Ethanol. Right. This is drinking alcohol. This is what is in alcoholic beverages. Okay. Ethanol. This is an alcohol. So 1, 2, 3, 4, 5 carbons on the main chain. Carbon number 2 has an alcohol group. Carbon number 3 has a methyl group. So what do we call this? 5 pentane. That's the main molecule. Okay, pentan-2-all, because you got to tell the reader that the alcohol group is on the second carbon. Pentan-2-all, but before 3.
Pentan-2-all, 3-ol.
It's a methyl group on the 3. It's a methyl group on the 3. So 3-methyl pentan-2-all. 3-methyl pentane-2-all. It's actually perfectly logical once you learn the rules.
Do you have a practice you need to work on?
I hate this.
Okay. Here's another group. Aldehydes. Aldehydes are just like ketones, but they're on the terminal carbon. So a ketone has to be in the middle of a chain somewhere. An aldehyde is the same functional group. It's an O8. It's a double bonded carbon. Sorry, double bonded oxygen. But it's at the end. It's at the terminal carbon. So there's a hydrogen hanging off because the carbon can have 4 bonds. So it's got 2 going to the oxygen, 1 going to the rest of the chain, and then hydrogen hanging off the end here. And so we don't need to number it because it's at the end of the chain. So there's no numbers needed, and we name it al for aldehyde, right? So if it has 7 carbons and an aldehyde group, it would be heptanal, okay? And so we just say al at the end. Al's hanging out there. In ether. Okay. Main chain functional groups. We're continuing now our walk through functional groups. Now we're talking about ones that aren't sticking off the side somewhere, but are in the middle of the chain. So now these ones interrupt the carbon chain. Okay. So ethers. Ethers are an oxygen in the middle with a carbon chain on either side. And it's just an oxygen. Oxygen, remember, can only have 2 bonds. So there's a carbon chain, and then instead of a carbon, there's an oxygen, and then a carbon chain that keeps going on. That's an ether. Ethers are very, very volatile. They tend to have really low boiling points, and ethers tend to become fumes and vapors very quickly. And so a lot of times, things that need to be aerosols and in the air will be built as an ether. It replaces the carbon in the main chain. We name each side of the chain independently. So like if there's 4 carbons on one side of the oxygen and 3 carbons on the other side of the oxygen, we would say butane, propane, ether. Right? 4 on one side, 3 on the other, and then we just say ether at the end, because that lets us know why we have two names. There's 4 on one side and 3 on the other. A carboxylic acid is a carbon double bonded to an oxygen, and then an alcohol at the end of the group, at the end of the chain. So it's terminal, oxygen, double bond, and then an alcohol. Okay, so this is like an aldehyde plus an alcohol, and we call it a carboxylic acid. And these are very common in organic molecules. Lots of the things that wind up being categorized as fat, lipids, oils, waxes, they're carboxylic acids. Okay, even a lot of sugars are carboxylic acids. So it's a double bonded oxygen and an alcohol group. And biochemistry really likes this terminal group because it gives a lot of places to start working on the molecule. There's a lot of ways to attack this molecule. You can attack the alcohol portion of it. You can attack the double bonded oxygen portion of it. It's a lot of work on organic compounds. So we name whatever the molecule is, and then we say oic acid at the end. So if there's 6 carbons, and then the last carbon has a double bonded oxygen and an alcohol, then that would be hexanoic acid. We put oic acid at the end to let the reader know that this group is there. Okay, so here is 1 carbon and 2 carbons separated by an oxygen. So this would be methane, ethane, ether. Oh, we say methyl ethyl, sorry, methyl ethyl ether. Methyl ethyl ether. That's fun. Here's 1 carbon, 1, 2, 3 carbons. So this is methyl propyl ether. Only counting from this side, 1, 2, there's a methyl group. So this is 2 methyl propyl methyl ether. Or you could do it the other way around, methyl propyl methyl ether. But it's, so on the propyl, there's a methyl group, and then there's this methyl group, and then there's an oxygen in the middle. I guess I started counting from here. That doesn't make much sense, but I guess I did. Started counting from here. 1 methyl propyl methyl ether. I think that's, well, but that is a smaller number than 3. Either way, I'll go either way. It's the same thing. Okay, here we go. Here's another one. So this is something with 1, 2, 3, 4, 5. It does 5 carbons, and the 5th carbon has a carboxylic acid group. So this is pentanoic acid. Oops, backwards. Okay. Here's 1, 2, 3, 4, 5, 6, 7 carbons. And if I start counting from here, I have an alcohol group on, oh sorry, I have carboxylic acid on 1. I have 2 methyl, 3 methyl groups. 1, so 2, 4, 5, or I could say 3, 4, 6. Oh, that's right. That's why I started counting from this end. Because it's carboxylic acid, that has to be the last carbon. There you go. That's why. So start counting from this end. It's a ketone on 2, and methyl groups on 3, 4, and 6. So ketone group on 2, methyl groups on 3, 4, and 6. 3, 4, 6 trimethyl heptan, because there's 7 carbons, no double bonds. 2-one, because there's a ketone on 2. Oic acid, because the last one is a carboxylic acid group. 3, 4, 6 trimethyl heptan 2-one oic acid. Good times. Terrible times. No, this is fun. Once you learn the rules, it's perfectly logical, and it always works the same way. Okay? So you just have to learn the rules. God bless you. I think this is your last one of text. I think it's your last one of text. The last couple of these are more examples. So here we go. So a carboxylic acid is the terminal carbon with a double bonded oxygen and an alcohol group. If instead of being the terminal carbon, if that structure happens somewhere in the main chain, then it's an ester. And so carbon double bonded to an oxygen, single bonded to another oxygen, and then the chain goes on. These are almost always found in something that's supposed to smell or taste good. Your nose and taste buds interpret these as happy. And so these things smell good. Most of the time you find them in perfumes and in food. We name them like an ether, where we name both sides, but instead of putting ether at the end, we put OH at the end. And we always name the one stuck to the oxygen first. So if this side had 3 and this side had 4, then it would be propyl butyl propyl butanoate, or something like that. And so we named the oxygen side before the carbon side. So this has 2 carbons attached to the oxygen, 1, 2, 3, 4 carbons attached to the carbon side. So this is ethyl butanoate. Okay. This one has 1, 2, 3 stuck to the oxygen, 1, 2, 3, 4, 5, 6, 7 stuck to the carbon. So propyl heptanoate. Okay, so that's how these work. We'll do this last slide on Monday. Or no, okay, the last group was a nitrogen-based functional group. So when you stick a nitrogen in a carbon chain, either on a side branch where instead of a hydrogen, you take the hydrogen off, you stick a nitrogen there, and then the nitrogen has 2 more hydrogens off the side of it. That's called an amine, or you would call it amine as well if the carbon were replaced by nitrogen in the main chain. So if it were nitrogen or carbons and then a nitrogen and then carbons, it's called an amine. So that's very common in genetic molecules, particularly if you have an NH2 group replacing the alcohol of a carboxylic acid. So it's a carbon double bonded to an oxygen and then an NH2 at the bottom. That's called an amino acid. And of course, you remember from biology, amino acids are all of the genetic molecules in your body, DNA, RNA. Those are all organic molecules with that amino group floating at the end. Okay, I think I have a couple of pictures for examples here, but I think this is, you're still writing, so I'll pause here.